Hello, everyone, and welcome to this problem session for worksheet 11 of the HoTTEST summer school. We'll go through some of the exercises, maybe not all of them because it's quite long. And most importantly, I think we should prioritize your questions underway. So if there are any questions that come up, just feel free to unmute yourself and ask them. Otherwise, we can also chat after the recording is done afterwards. Okay, so let's start with thinking about exercise 1. So we're given 3 types, A, B, C, in our universe. So in the exercise sheet, we write type in bold, but on paper, we usually write U. I mean, some people write that in LaTeX as well. Now we had this function, equiv_ev. So equiv, which takes a path, so something like this, and returns an equivalence, B there, defined by path induction. So it sends the reflexivity on A to the identity self-equivalence on A. So this function is parametric in the types A and B, and so we can define it by path induction. And this is how we did that. So the first point here, I should have written A, B, C, but it's A here, so it's 1.1, I guess. It asks us to show that equiv_ev of the reflexivity path is equal to the identity. And this just holds by definition. That's how we defined equiv_ev. So it's kind of a stupid question, but it's intended to make you remember the definition, essentially. So holds by definition. So there's you could put a dot over there. Now, the second point asks us to show that for all paths P from A to B, and let me write this out properly, and Q from B to C, we have that equiv_ev of the composite path is equal to the composite of the corresponding equivalences. So fortunately or unfortunately, path composition is written in inverse order to function composition. So that's why they're swapped here. And this is showing that equiv_ev is in some sense functorial. That composition of paths corresponds to composition of equivalences across this equivalence, equiv_ev. And now again, to define such a path, I can induct on both P and Q. So induct on P and Q. Then we get, the goal becomes equiv_ev. And depending on how you defined path composition, you could have that refl A composed with refl A is just definitionally equal to one copy of refl A. So A is a definitional left or right unit for path composition. And if it wasn't definitional, then you would just insert another path. But let's work with this. And then on the other side, we have equiv_ev of refl composed with equiv of REFL, and by the previous point, this is the identity at A, and we're asking for an identification with the identity at A composed with identity at A, and this is easier to show by function extensionality. These two functions are equal. Okay, so I'm going to scroll a bit. No, it wants me to just jump the page. No, okay, I can do like this. Okay. Now, finally, the last point wants us to show that for all P, equiv ev of P, when I invert the path P, is equal to equiv ev, where I do the inverse equivalence. So all the things we're proving here are sort of functoriality type things. And again, we can induct on P. And the goal becomes, well, on the left-hand side, equiv ev, the inverse of REFL is REFL, definitionally. So this is REFL A, if you will. And on the other side, let me just write it out by by 1, equiv ev of REFL computes to identity at A, and then this is the inverse of the identity at A. And it's straightforward to show that the identity at A is its own inverse. So this here is the identity at A. And so identity at A is equal to identity inverse at A. And that's how you conclude 1-3. Okay, so up to here, I didn't assume that the universe U was univalent. And recall, maybe let's recall that. Recall U is univalent if equiv ev is an equivalence. And so equiv ev lets you create an equivalence out of an equiv ek. I'm writing ev everywhere, and it should be ek. Yeah, sorry about that. So equiv ek. It shouldn't be ev. I've been making that mistake consistently, so I'm not going to go back and fix it. So it's saying that equiv ek, which constructs an equivalence out of an equality or an identification, is an equivalence, so that from any equivalence we can get back a path or an identification. And now this second part of the exercise is asking whether these equations 1, 1, 1, 2, 1, 3 also hold for equiv ek. No, for ek equiv, the inverse. And you can prove all of those by essentially, since it's an inverse, it's going to hold, it's going to satisfy all the same things. So the equations 1, 1 to 1, 3 hold for ek equiv 2. So let's take an example. So let E be an equivalence now from A to B. Then let's show this 1, 3 that if I invert the equivalence, that corresponds to inverting the path corresponding to this equivalence. And I'll show that like this. So we do now equiv of E inverted. That's the same as equiv. Now I'm going to have to insert some things here. I'm going to write equiv equiv E inverse. So here I'm changing E with the round trip back and forth along this equivalence. And this is equal to, well, by the thing I proved above, I can put this inverse here. I can put it as path inversion. So here I get equiv and here I'm going to get the inverse of this path, E. And now I can cancel these outer two equivalences. So this is equiv E. And so I've shown that equiv of the inverse of an equivalence is the same as the path inverse of the path corresponding to that equivalence. So that's what this exercise is asking for. And similarly, you can do 1, 1, and 1, 3, or 1, 2. Okay, I hope that is more or less clear. Maybe any questions before we proceed? Sorry about this equiv-ev confusion. Okay, so I think I'll jump straight to exercise 3 now, which is a quite substantial exercise and an important one. So we're going to start by assuming our universe U is univalent. And yeah, we're going to see that interesting things happen. So the first thing we're going to do, again, this is 1, so 3, 1, I guess. So we want to show that the type of types which are contractible, so is contour X is contractible. So that's the first thing we're going to do. And yeah. Yeah, so I'm just going to give the proof that, like, this is saying that sort of the universe of contractible types is itself contractible. And we can recall that a type X is contractible if and only if the map down to the terminal object. So Egbert writes this with a bold one. The map, so there's a unique map down to the terminal object, is an equivalence. So using this, the type we had above, X in U, such that is contour X holds, is equivalent to the type of X in U such that X is equal to 1, or X is equivalent to 1, sorry. And by univalence, this is in turn equivalent to x in u such that x is equal to 1. And this latter type, this guy here, is contractible. With center, so maybe let me write that out. Center, you take the identity or the unit type with its trivial identification to itself, REFL 1. So this is in the book. Similar things were used in the lecture yesterday, but this is also a consequence of exercise 4 from worksheet 3. If you go back or if you recall that exercise. Yeah, and it's not, if you sit down and think about it, making this contraction is not very difficult either. Okay, so that's 3.1. And this exercise 3 gets progressively harder. So let's keep our momentum. Now we're going to show that the universe of k truncated types or k types is itself k plus 1 truncated. So show that I'm going to write, I guess, let k be greater or equal to -2. Yeah, so this thing that truncation levels we start counting them at -2. It might be it should be getting more intuitive by now, but at first it seems like a very puzzling thing. And so k is a truncation level, and the lowest truncation level is -2. If you're -2 truncated, then you're contractible. If you're -1 truncated, then you're a proposition. If you're 0 truncated, then you're a set. If you're 1 truncated, well, then you're 1 truncated, or you're something groupoid-like, and everything above we just say you're k truncated, or you're a k type is another way of saying it. So now I'm defining the universe of k types. So this is all types x in our given universe, such that this proposition is trunc k x holds. So we're going to show that is itself a k plus 1 type. And recall that this is trunc. Maybe I should recall. So let me do a sidebar on that. Recall is trunc is defined inductively, and is trunc -2. X is defined by is contour. And is trunc k plus 1, so we're defining it inductively, is well, one way to define it, I'm not 100% sure if this is how it's done in the book or in the lectures, but one way of defining it is to say that for any two objects in X, two elements or terms, the path type is trunc K. The path type is K truncated. So that's how S-trunc is inductively defined. And now we're going to show that the universe of K types is itself a K plus 1 type. So for K, when K is equal to -2, we just showed then this universe of -2 types or contractible types is exactly the type we considered in 3.1. And we show that it is contractible. So it's not only a K plus 1 type, it's actually a K type. So we saw that u minus 2 is contractible. So we're done for this one case. So let k be now greater than minus 2. Then we need to show that for any two types, x and y, in the universe of k truncated types, the identity type x is k truncated. Now I'm cheating a tiny bit here because x and y, I'm writing them as just types, but they come equipped with a proof that they're a k-type, or that they're k-type truncated. But this proof is a proposition, so I don't really need to give it a name. It's if it exists, it's unique because it's a proposition. So I could have written these as tuples, but I'm not. Now there's a map which forgets about the proof of truncatedness and just goes into the universe. And this map is an embedding. No, sorry, it's not an embedding. It's an equivalence, because the equality of the proofs of propositions, or the equality on proofs of truncatedness is trivial. So this map is an equivalence. And we know that the equality type between truncated, well, I guess maybe I'm stating that to the type of equivalences between x and y. And this, we know, is a k-type. So I just got a message that my connection is unstable. Has it been fine, or has it been jittery? Could anybody say? Oh, there are things in the chat. Okay. I wasn't paying good attention to the chat. Evidence, yeah. Okay. Okay. Okay, I'll pay more attention to the chat from now on. So sorry about that. Okay, so we just showed that it was interrupted for a second. Okay, so we just showed that when k is greater than minus 2, what we need to show is that for any two k truncated types, their path type is k truncated in the universe of k truncated types. But this path type is equivalent to the ordinary path type in the universe, which is equivalent by univalence to the type of equivalences from x to y. And this is a k-type. Essentially, we know that functions between k-truncated types is itself k-truncated, and it follows quite easily that equivalences between k-truncated types also form a k-type. So that concludes 3.2. And now we come to 3.3, which asks us to show that the universe of propositions is not a proposition itself. So show that u minus 1 is not a proposition. Note that in 3.2 we showed that it's a set, it's zero truncated, and here we're asked to show that it's strictly a set. It's not less than a set, i.e. a proposition. So what do we need to do? Well, we need to show that not all elements of the universe of propositions are equal. So yeah, it would be weird if it's a proposition, because it would mean that all propositions are the same. Yeah, so somebody's commenting that it would be weird if this universe is a proposition, because that would mean all propositions are the same. But all propositions are not the same. In particular, we're going to show that false is not equal to true. So consider the empty type and the unit type as elements of the universe of propositions. We're going to show that they're not equal. And so what does that mean? We need to show that if they're equal, then we get a term of the empty type. So suppose, let's say 1 is equal to 0, or empty. Let's give the term a name. Then we can transport along this path. Yeah, let's see how I want to say this. Yeah, so first of all, this is an identification in the universe of propositions, but by the argument we have on the top of the page, this is the same as just an identification like this. So now we can transport along T, so that T of the only element of the unit type is then an element in the empty set. So the family that I'm transporting along is the identity family from the universe to the universe. Well, okay, no, let me write this a bit more understandably. So I have this then equiv ec. Let me get it right this time. So equiv ec is now a function or an equivalence from 0 to false. So we can evaluate. Yeah. So equiv ec T at the only element of the unit type is then an element of the empty type. So we've shown that if you have such an identification, you get an element of the empty type. So we've constructed a function into the empty type, and that's exactly what it means for this to not hold. Yeah. Okay, so now we come to the last part of this exercise, which is also the most tricky one. And we're going to show that the universe of sets is not itself a set. Yeah, so somebody's foreshadowing in the chat here. They're saying that we should use the two equivalences from bool to bool. And they typed bool wrong incorrectly, and it turns out in the solutions I also typed bool incorrectly. I usually use the bold 2 element sign, but at one spot here I think it's literally written bool. So yeah, I hope that's not too confusing. So we need to show here that the path types of the universe of sets are not propositions. So what does it mean to not be a proposition? It means you have 2 different elements. Not all elements are the same. So we need to show let's say, consider. So this is 2 is certainly a set, and we're going to consider the this path type here. We show that it's not a proposition. It's by exhibiting 2 distinct elements. Okay, so we have a swap function from bool to bool. And it's not just a function, it's an equivalence. And it sends 0 to 1 and 1 to 0, or it's the successor function, as Egbert was calling it yesterday, if you're thinking about mod 2 arithmetic. And so we get here we need to do equiv swap. This is by univalence now. We get a path from 2 to 2 in the universe. And by the argument that we saw above, this is the same as the identity type among sets. So we need to show that this is not the reflexivity path, or want to show that equiv swap is not equal to refl. Okay, so suppose it's equal. Equiv swap is equal to refl. Then this implies that swap is equal to the identity. So here I'm passing across the equivalence, and we saw that refl corresponds to identity. That's what we saw in the first exercise. And so this type again, we know that this type is equivalent to the type of homotopies. So x into, this is function extensionality I'm using now, that x into swap of x is equal to x. That's identity applied to x. So if we supposed an element here, we certainly get a homotopy age like this. Now we can evaluate age so that we get age at, let's do, I think I want to do false or 0. So now this is a path from true to false in the 2-element type. And in a previous worksheet, so this is exercise 3 in worksheet 5. We saw that this equality does not hold. So from this, you deduce, you get a term of the empty type. And so we're done. We've gotten a term of the empty type. Okay, so that's a long and technical and very important exercise, actually. And if there are any questions, feel free to write them in the chat or speak up. Okay, then I think I will continue to exercise 4. Oh, here's a question in the chat. Right. Not really a question, but a comment. Okay, I should scroll up. Yep. So to the beginning of 3 or to the beginning of 1? 3, 4. Okay. Great. You are welcome. So now we are we're continuing along this line of showing that certain statements are false, which might feel kind of new and is kind of cool, I think. So we're asked to give an example. Well, actually, in terms of time, there's no way I'm going to cover this one and some of the other things I want to cover. Well, actually, let me cover this one and then skip right to the last one. Or does anyone have a preference for 4 over 5? Maybe write in the chat. So in the absence of any preferences, I'll do 4 and then 6, I think. So give an example of a type family like this, such that this implication here does not hold. So I would prefer 5. Yeah, I mean, slightly me too. No, it's not too late. It's not too late. So let's go straight for 5, and maybe if there is time, we'll come back to 4. So let's go for 5, which I think is a really cool one as well, and gets into doing homotopy theory. So let's do that. So let A be a type. Then we write B odd A for what's called a path component of A in the universe. So these are all X in U, which are merely equal to A. And if I didn't put the truncation here, then this type would be contractible. But if I put the truncation there, then this type turns out to be very interesting. And it's the path component of A in the universe is one way of saying it. And we saw this one a bit, or a similar one earlier. We saw the path component of the unit type. This was the universe of contractible types. And we saw the path component of the unit type is itself contractible. That was what we saw in 3.1, if you want to think about that. And now this first thing here is asking us to show that, or to characterize the identity types in the path component. So for 2 tuples like this, and now I'm not cheating, I'm writing out the tuples with these proofs of being merely equal to A. So for 2 such things, yacht A, we want to show that there are type of identifications in B odd A, Y, Q. Yeah, so what does B odd stand for? That's a great question. And well, the first answer is B odd is a notation that comes from topology. And the B stands for classifying space, or it's the notation usually used for something called a classifying space. And if you write B something, it means that when you take the loop space of that thing, you should get, you should essentially cancel the B. And so we're going to see towards the end of this exercise that when I take the loop space of B odd A, I get odd A, which is the type of automorphisms of A, or self-equivalences of A. And so in terms of this summer school, it's a bit early to explain what B odd means or what it is. But for now, you just think of it as a notation that turns out to have roots in topology and homotopy theory. So if you want to not write B odd and just write out the sigma type, that's of course also fine. Okay, so right. So by characterization of paths and sigma types, this left-hand side here, it's a path of dependent pairs. So it's a path on the between the first components, y, which transports in a certain way. So let me just say there's a cloud here, and what the cloud is written out in the solutions. But the point is that this cloud ends up being a path in a proposition, and so this it's contractible. So this cloud is contractible, is all I'm saying. And so when you do PR1 here, that's an equivalence. And for a bit more details, look at the exercises, but this is what's really going on. Now, let's deduce something. So we're gonna, so then we get, so we have always an element of B odd A, and it's A itself. A, of course, lives in its own path component. So A, REFL A, is an element of B odd A. And we're going to compute the what's called the loop space, so the space of identifications of this point to itself. So, and we get, so A, the space of identifications in B odd A from A to itself, A. By the previous point, this is the same as the self-identifications, or self-identifications of A in the universe, which by univalence is equivalent to the self-equivalences of A, which is how we define the notation ought A. So this is where the notation comes from, essentially. That when we took this loop space here, so identifications from the point to itself, we got back ought A. That's what the notation is trying to make you help you remember. Okay, so now we're going to show that B ought A is connected. And connected is not something that's been defined in the course, but I'm defining it in line here. And of course, it makes sense that the path component of A is connected. The path component should obviously be connected. So we're sort of justifying the terminology here. And what does it mean? It means that for all, let me write X and Y in B odd A, we merely have that there's a path from one to the other. So if there was an actual path, that would mean that B odd A is a proposition, but we're just merely asking for a path. And that's what connectedness is. So it's not saying you can continuously choose a path or something like that, which would imply simply connected and that higher homotopy vanishes. It's just saying that there exists a path, you might not be able to choose it. Okay, so right. yeah, so by A, we have that X is equal to Y. Right. This is equivalent to A in the universe. And we can construct an element on the right-hand side. So I see there's a question in the chat. I'll get to it afterwards. We have, so I'm gonna halfway cheat a bit here. So we have X. We have this, I didn't give it a name, but we had an identification P, which is not an actual path from it's not an actual path from A to X. So let's recall the definition here. We have these mere paths from A to X and A to Y. And they're not actual paths, but they're mere paths. But I can compose and invert these mere paths. So I have a mere path here. And I have a mere path here. And these, when I compose them merely, and this is what we show in the exercise 2, you get an element here. And I think that's all I can say about that now. These are homotopy classes of paths, and you're composing homotopy classes of paths essentially. Well, no, even worse. They're mere paths. The homotopy classes would be in a set truncation, whereas here it's a propositional truncation. So look at exercise 2 to understand this better. But by composing these two mere paths, we get an element of the right-hand side here, which is what we needed to show connectedness. Okay, so now there's a question in the chat. It's the only way of giving. So they're asking if the only way of giving a path here is by giving actual paths and wrapping and using the truncation. And my answer is no, because P and Q might not be actual paths, but you can still construct a function which merely composes them, and that's sufficient. So that's what we did here, and exercise 2 explains that in more detail. Okay, so now the end of the exercise, we're going to show that the loop space of B02. So now take A to be bool. Then yeah, so then we take 2 with its identity self-identification. In B02 with its identity identification. We want to show that that's equivalent to 2. So this is showing that the loop space of B02 is the 2-element set. And another name for this is sigma 2, or the symmetric group on 2 elements. So that's where the automorphism, the bijections of a 2-element set are themselves a 2-element set, and that's the symmetric group on two elements. So this is also justifying this notation, and it's a concrete computation. So this is this follows from what we just did and exercise 5 in worksheet 10. So, right. So it follows from what we just did in exercise 5B, worksheet 10. So now there's a question that asks me to show where things would break down if we didn't truncate the path in the definition of B-aught. And just to clarify, you're asking about this exercise 5 and not exercise 5 of the previous worksheet, this exercise 5. Yeah, so if we didn't truncate, then everything would break down. So let me explain that by maybe putting a different color here. So if I didn't truncate, then the type would be this, A is equal to X, but that's contractible. So if I didn't truncate, it would be a contractible type. I couldn't do any, these path spaces would be all trivial. They would be contractible types, and everything would break down. Okay, but maybe they're asking, it's contractible because, well, it's the total space of this. Yeah, what's the right reference for that? What is the right reference for that? It follows from the fundamental theorem of identity types. So this is contractible with center a REFL. So that's contractible by this worksheet 3, exercise 4 or something, for example. Okay, you can use the second component to make the first components equal. There are many ways of proving it. If you look at, it certainly is part of the fundamental theorem of the identity types in the book. That's one place you could look, or worksheet 3. That's another place. But constructing a contraction, you can just do it directly. It's not hard to see. Whereas if you have just a truncated path, then that doesn't work. Okay, so we're getting to the end of our time here. I won't have time to go through 6, but let's keep taking some questions, and then I'll stop the recording. Are there any more questions for now? Okay, I'll stop the recording and we can discuss. Right, okay, I'll do the beginning. So 6A, I'll do 6A, and then we'll stop the recording. So let's do that. 6A. So, so we begin by recalling, if we're giving a type A, and some type family over A, and some A in A, then we have this sort of type theoretic unita lemma, which says that this right-hand side, which you should think of as natural transformations from the HOM of A, or the identity types of A, is equivalent to P at A. So this is the type theoretic unita lemma in theorem 1333 in the book. Now, the first thing we're asked to show is that if the total space of P is contractible, then we can improve this equivalence. So let me see if I can just copy it. Improve it. That was slick. And put an equivalences here instead. So it's just upgrading the statement, in a sense, to put equivalences here instead of just natural maps. Okay, so note a family like this. B is an equivalence if and only if it's an equivalence on total spaces. So if I call this eta, then the induced map on total spaces, B A is equal to B, AP is an equivalence. That's theorem 11.1.3. Now, since the left-hand side is contractible, that's this fact that we were discussing above. This happens. So since the left-hand side is contractible, and the right-hand side is also assumed to be contractible, right-hand side, this is automatic. Any map between contractible types is an equivalence. This is automatic. So eta is a family of equivalences. So I should have written family of equivalences. A family of equivalences. So the reference here is theorem 11.1.3. It's a very important fact that families of equivalences are exactly the ones that induce an equivalence on the total spaces. Okay, and that this trick or this lemma goes into showing that you have a UNITA embedding in type theory, which is the part B of that exercise. Okay, I'm going to stop the recording here, and we can chat a bit afterwards. So stop recording.